So mapping and following the energy change in a system is important to us. Sometimes it's okay just to use those LOL graphs or the bar charts to follow it along, because we just want an idea of where the energy is going or if it's coming in and how it's affecting the system, through a phase change or a temperature change. That's okay for the most part, but sometimes we really do need to have a physical number, a representation of how much energy has gone in and out, not just an idea, but the actual amount. So those LOL graphs don't necessarily work out for us, and that's when we have to get down and start working on calculations with energy. And in these notes, we're going to look at two different equations, and the reason we have two different equations is because we have two things going on. We can change the phase, and we can change the temperature, and each of those takes a different amount of energy. So, looking at our graph here, and this is very similar to the one that you did in the Icy Hot Lab, where we had the cup of ice and we sat it on the hot plate and put a temperature probe in it and just kind of graphed what happened to the temperature throughout that whole thing. So what we see in these regions here, on the sloped regions, we have temperature. And in this case, we are adding energy into the system, so we see that the temperature is going up in these two regions. However, we had areas like here and here where it was flat and the temperature didn't change, but we were still pumping energy into that system. It's not like the hot plate stopped working over those periods of time, but we didn't really notice a temperature change. It leveled off at that area. And this is where we see a phase change. Those solid ice particles melting into the liquid, or the liquid water turning into the gas and boiling away. That takes energy. It takes energy to break apart that solid structure and move into the liquid phase, or it takes energy to break that barrier between the liquid and the gas and set those gas particles free to float wherever they want. Looking at both of these, we are going to have to adjust our equation, because calculating here and here is different than when we're looking at a change in temperature here and here. This is what we're going to focus on, is the calculation of the energy used in each of these portions of the graph. All right, let's first start out by looking at the phase changes, and this portion happens on the flat part of the graph. We have heat of fusion, which looks at the melting, freezing, so this is the lower flat part, and then we have heat of vaporization and condensation, which is the higher portion of our temperature and time graph. To calculate this, we have the energy equals mass times heat, and heat is this heat of fusion or heat of vaporization. It is important for you to realize that in different areas of that graph, we use different heats. So if we have our graph here, we would do fusion, and up here we would do vaporization. For heating and cooling, the sloped parts of the graph, we have to use what's called heat capacity. And heat capacity is different depending on what type of substance you're looking at. So if we're looking at solid water, it takes less energy to raise a gram of the substance 1 degree than liquid which takes a little bit more energy. So the heat capacity is the amount of energy it takes to raise 1 gram of the substance 1 degree. So if we only have 1 gram of water, and we wanted to go from 0 degrees Celsius to 1 degree Celsius, it would take 4.184 joules of energy to do that. So every time we take that 1 gram up a degree Celsius, it takes this much energy to do that. Now, for every gram we have, it takes this much energy. So if we were working, say, with 10 grams, to go up 1 degree Celsius, it would be 10 times this much energy. All right, when looking at changing temperature, this is the equation that we have for changing temperature. And again, this is for the sloped parts of the graph. Q equals the heat, the energy that you're looking for. Mass is pretty easy. It's just the mass. The heat capacity, this is where you fill in that known. And then we have the change in temperature, and that is final minus initial. Sometimes this is going to be negative. If you start out at a temperature of 100 degrees and drop the temperature to 50 degrees, your final is 50 degrees. Your initial is 100 degrees. Your change is negative 50 degrees. That's fine. It's okay. It means you have a negative energy, and energy was leaving the system. That's what that negative means, is that it was leaving the system. So sign is very important here. We'll circle that in a different color so you can see it. Sign is important. Make sure that you show your work, or it will show that you had either a loss of energy or a gain of energy. Okay, so let's try an example. We're going to go back to that coffee cup example because it's pretty easy for us to understand. If it starts at 75 degrees Celsius and comes down to room temperature at 20 degrees Celsius, how much energy did it release into the system? So first things first, we need to figure out what is the change in temperature. Well, you take the final, 20 degrees, minus the initial 75 degrees to get your change in temperature. So change in temperature equals final minus initial, or 20 minus 75. And then we're also going to use the CP for water, because the CP for water is, coffee is pretty much water with a little bit of flavoring in it. So we can use this. So here we have the calculations for the change in temperature. Since we have liquid water, we are going to use 4.18. Our mass from our problem was 140, and we are looking for Q. So we just plug everything in. 140 goes in for mass. CP is 4.18. Change in temperature is negative 55. Do the calculation out. We get negative 32,186 joules, which is kind of a big number. If we round that to significant figures, we get 32,000 joules. A lot of times we just reduce it down to kilojoules for ease of reporting, so it's negative 32 kilojoules, or negative 32,000 joules was released. And we know that it's released because we have this negative here that tells us the energy left the system. It was subtracted from the system. Okay, another one. Suppose during a volleyball practice you lost 2 pounds of water due to sweating. If all of this water evaporated, how much energy did the water absorb from your body? So 2 pounds of energy evaporated. This is a phase change. You're not really changing your temperature, you're changing your phase. This causes us to lose that energy. So first things first, we have to have mass in grams. So we do a little calculation and we come out to be that 2 pounds of water is really 909.1 grams of water. Then we need the heat of vaporization, which is 2,260 joules per gram. So it takes 2,260 joules to turn 1 gram of water into a gram of steam. If we go and do our calculations with this, we have the energy equals mass times heat. So we put our mass in as 909.1 grams, and then we have our heat, which is joules per gram. We get a very large number of 2,054,566 joules. Convert that into kilojoules, we get 2,055 kilojoules would be our answer. So again, since this is positive, we have this much energy went into the water. Well, this energy came from somewhere, and it was energy that came out of your body as you were exercising. So this helped remove some energy from your system, causing you to be cooler and helping to control your temperature. So even though we were looking at a phase change, this is the process, or this is why our body goes through sweating, so that way we can reduce the amount of energy in our system and keep us cool.